Hello everybody, I'd like to introduce this presentation regarding the Latin square design. But in this presentation, the Latin square design with missing data. And sometimes this design is called incomplete Latin square design because of the missing data. For the complete design, you can return back to the previous video for the Latin square. This is our question here. There is an industrial engineer is investigating the effect of 4 assembly method. So we have 4 assembly methods denoted by letters A, B, C, and D on the assembly time for a color television components. So the assembly time is the dependent variable, and the treatments is simply the assembly methods, which are A, B, C, and D. 4 operators are selected for the study in order to control for this variable, because there are some deviations between each 2 operators, so we need to control this factor or this variable. The other factor, furthermore, the engineer knows that each assembly method produce such fatigue that the time required for the last assembly may be greater than the time required for the first. So this is the other factor we need to control by the Latin square. So the first factor or first variable is the operator, and the second one is the assembly order, as shown in the below table. A trend develops in the required assembly time. To account for this source of variability, the engineer uses the Latin square design, analyze the data from this experiment at probability of 0.05 and draw appropriate conclusions. So here we have the Latin square table. As you see here, we have 4 assembly order, and we have 4 operators, and inside this table we have 4 treatments A, B, C, and D, and the number along with the letter represent the time for the assembly. For example, this value here means that we have the first operator who works in the first assembly order, who uses the treatment C. The time for the assembly for this operator is 10. As you see here, we have a missing unit or missing value or missing plot in row number 1 and column number 4 for the treatment B. So this is an incomplete Latin design. Before starting the calculations, this is the missing value. It is denoted by X. 1 for B. 1 here represent the order of the row. It's row number 1. The second number is 4 and represent the the operator or the column. So we have the column number 4, and capital B means that the missing unit for the treatment. So we have treatment B, but with missing value. First of all, we should estimate. We should make an estimation for this value, and the purpose of the estimation does not improve the analysis or supply some additional information. The purpose of the estimation is just to facilitate the analysis of the remaining data. So this is the purpose of the estimation of the missing value. Again, before starting the calculation, we need to understand the steps for the solution. First of all, we need to estimate the missing value. We will use something called Yates formula. This is the Yates formula. I'll talk about the details in this formula. The second step is to replace the missing value by the estimated one. Then we will do the analysis of variance for the data based on the standard procedure. Then we need to make a modification to the analysis. One of the modification is the subtracting 1 from the total and the error degree of freedom. I'll talk about it deeply. Then we need to compute what's called the adjusted SS for the treatments. So we'll have two ANOVA table. One is the initial, and the second is the adjusted and the recommended one. Then we will complete the adjusted ANOVA for the adjusted data. And finally, we can simply draw the conclusions. So the first step is to make the estimation for the missing value. This is called the Yates formula. There are many formulas for the estimation. This is called Yates formula. Xij is the estimation of the missing value in the ith row, jth column, tth treatment. And in our question, the missing value, as you see in the table above, it lies in the first row and the fourth column and for treatment B. So it's called X14B. The value T represent the number of rows, which is the same as the number of columns, which is the same as the number of treatments, and simply it is 4. R sub I represent the total of the units or observation in the row where the missing unit appears. And the total observation for the first row, where the missing value appears, is R1, which is equal to 31. And regarding to the column C sub j, it is the total of the units in the column where the missing unit appear. As we have said, the missing appears in column 4, so the total of the observation for column 4 is C4 is equal to 31. T sub k represent the total of the units or the observation in the treatment where the missing unit appear. The missing unit appear for treatment B, so the total of the observation for treatment B is equal to 29. Let us count for this value. In row 1, of course, there is no value for B because it is missing. In the second row, the value of B is equal to 7. In the third row, it is 10. And in the fourth row, it is 12. So the total is 29. And regarding the capital G, it is simply the sum of all the values or all the observation or the summation of x sub ij, and it is equal to 156. So now simply we can substitute for all of these values in the Yates formula. This is small t. This is the total of row 1. This is the total of column 4. This is the total of the treatment B minus 2 times G. This is the capital G, the total observation. T minus 1 multiplied by T minus 2, 4 minus 1 multiplied by 4 minus 2. So the estimated value, which is represented by X14B, is simply 8.67. So this is the first step in order to get the solution. The second step is to replace this estimated value in the missing cell, same like what we have here, as you see in the table above. This is the missing value or missing unit. We estimate it to be 8.67. Take care that the total of the observation for the first row, now it will change. It will increase by the amount of 8.67. And also the total observation for the column number 4, it will increase by the same amount. And finally, the total observation for all the observations also will increase by the same amount. And also again, regarding the observations for the treatment B, it will increase by 8.67 as we see in the below table. So after the estimation, the third step is to make the analysis based on all of these data. So now all the data are complete, so we can simply make the analysis. I have presented a presentation for the Latin square in a previous video. You can return it back. In this video, I will try to go quickly for the basics. This is the Latin square ANOVA table. The sources of the variation we have first for the treatment, and then we have for the rows, and we have for the columns, and we have for the error. We will count for the or calculate the degree of freedom and the SS and the mean square and the F calculated or F statistic, and we will determine the F critical and compare between these two Fs. Let's start with the calculation of the degree of freedom. So the degree of freedom for the treatments is simply equal to the number of treatments minus 1, which is 4 minus 1, which is equal to 3. The degree of freedom for the rows, and notice that the rows here represent the assembly order. It's equal to the number of rows minus 1, and it is the same as the treatment because we have a square here, so it's 3. So the degree of freedom for the column, and the column represent the operators, it's equal to the number of columns minus 1, same, we have 3. And regarding the degree of freedom for the error, simply we multiply r minus 1 times r minus 2. And r here represent the number of rows, which is the same as the number of columns, which is the same as the number of treatments. So r minus 1 is 3, multiplied by r minus 2, which is 2, so we have 6. The total degree of freedom, simply we can use this formula, r squared minus 1. So 4 squared minus 1 is equal to 16 minus 1, so it's 15. Simply we can add or sum up the degree of freedom total by adding up all the degree of freedom for the treatment and the rows and the columns and the error. So we will get the same as 15. We fill in the Latin square ANOVA table for the degrees of freedom as we have here. Now we need to compute for the values of the SS, sum of squares. Before starting the calculation of the SS, let's calculate the correction factor. The correction factor, this is the formula for the correction factor. Simply, first we need to get the total of the observations, or the capital G. We should square it and divide it by r square. R square are the number of observations. We have 16 observations, so it's 4 times 4. This is the total of the observations squared, divided by 16. So this is the value of the correction factor. Now we can calculate the SS for the total. This is the formula to compute for the SS total. Simply we need to take the summation of all the squared observation minus the correction factor. The summation of the squared observation, we have this value, for example. This value lies in the row number 1 and column number 1 and the treatment C. This is the second value squared, row 1 and column 2 till the end of the observation, which is 14. So this is the summation of the squared of the observation. Now we can calculate the SS total. This is the summation of the squared observation, and this is the correction factor. This is the value of the SS total, 150.41. Now we need to calculate the SS for the rows. And in order to calculate for the SS of the rows, we need to have the total of observation for row 1 and the total of observation row 2 and row 3 and row 4, and take the summation of this squared value divided by R minus the correction factor. So this is the value of row 1, and this is the sum of row 2. This is for row 3 and this is for row 4. We should square and summing up divided by 4, and this is the correction factor. So if you proceed, you will get the SS for the rows is equal to 17.92. The same way for the columns, we need to get the total observation for the first column and the second column and the third column and the fourth column. So now we need to have the summation of the records in the column. This is the sum of column 1. This is for column 2. This is for the 3. And this is for the fourth column divided by R, which is 4, minus the correction factor. So the SS for the column is simply 50.92. Now we should calculate the SS for the treatments. And in the table up to the right, we have the sum for the observation for each treatment. For example, for treatment A, it's 30. For B, it's 37.67. And for C, it's 53. And for D, it's 44. This is the formula to calculate the SS for the treatment. This is the total observation for treatment A. This is for treatment B. This is for treatment C. And this is for treatment D. Divided by R, which is 4, minus the correction factor. If you proceed, you will get the value of the SS for treatment is 71.25. Now we can simply calculate the SS for the error after knowing all the SS, because the SS total is simply it's equal to the SS for the treatments plus the SS for the rows plus SS for the columns plus the SS for the error. The SS for the error is the unknown value here, so we can compute for it by using this formula. So this is the SS total, and this is the SS for the treatment. This is the SS for the rows, and this is the SS for the columns. So this is the value for the SS of the error. It's 10.32. By this, we finish all the calculations for the SS. Now we fill all these values in the Latin square ANOVA table, same like what we have here. Now we need to calculate for the mean square, which is abbreviated by MS. The formula to calculate for the MS is simply by dividing the sum of squares by the degree of freedom. So for the mean square of the treatment, we should divide the SS of the treatment by the degree of freedom for the treatment. This is the SS for treatment, and this is the degree of freedom for the treatment, and this is the mean square of the treatment. The same way for the rows, this is the SS for the rows, and this is the degree of freedom, and this is the MS for the rows. The SS for the columns, degree of freedom for the columns, so this is the MS for the columns. And finally, the MS for the error, this is the SS for the error, and this is the degree of freedom for the error, so it's equal 1.72. Now we need to calculate for the F statistic or the calculated F. We need only to have the F for the treatments, because the Latin design is already control both the rows and the columns. And the Latin square design consider that there is no interaction between the treatments and the rows and the columns. To calculate for the F, simply we divide the mean square of the treatments by the mean square for the error. This is the MS for the treatment, and this is the MS for the error. So this is the value of F for the treatments, 13.81. Now the remaining is to find the value of the F critical for the treatments. And in order to determine this value, we need to know three things. First, we need to know the probability, which is simply the area right to the F critical, which is equal to the significant level, which is 0.05. It's already given in our question. And we need also two values for the degrees of freedom. The first one is called the degree of freedom in the numerator, which is simply the degree of freedom for the treatments, which is 3. And the second degree of freedom, which is called the degree of freedom in the denominator, it is simply the degree of freedom for the error, which is equal to 6. So we need this value. We need to get the F critical for the treatments for probability of 0.05 and 2 degrees of freedom 3 and 6. So we can simply return back to one of the F distribution table for a probability of 0.05, same like what we have here. This is the table of the F statistic for a probability of 0.05. In this row, we should have the degree of freedom for the treatments, which is 3. And in the column here, we should have the degree of freedom for the error, which is equal to 6. So the intersection between these two values is simply the F critical, which is equal to 4.76. So the F critical for probability of 0.05 and degree of freedom 1 equal to 3, and the second is equal to 6, is equal to 4.76. So by this calculation, we fill all the needed values for the ANOVA table, but notice that this is an initial table. This is not the final one, simply because we add the estimated value, so we need to make some adjustment or some correction. If you check for the significance, we simply see that the value of the F statistics is greater than the F critical. So we have a significance here, but we are not interested in this table. This is the initial one. So we need to make some adjustment or some correction. First, for the SS, for the treatments. So this is the formula how to get for the adjusted value of the SS for the treatment. It is simply equal the initial value of the SS for the treatments minus some value. Regarding this value, capital G here represent the marginal total or the total observation. Notice that this is the original table where we have a missing value here in row 1 and column 4. So capital G is equal to 156. R sub I represent the row where the missing value appears. It is in row 1, so the total of row 1 is 31. C sub J here represent the column where the missing value appears. So we should take care of column 4, and the total of column 4 is again 31. T minus 1, T represent the number of rows, same as columns, same as treatments, multiply by T sub K. T sub K here represent the total observation for the treatments, treatment B, because the missing value is related or belonging to treatment B. So for treatment B, the total, which is T sub K, is equal to 29. If you count for the total for treatment B, notice that in the first row we don't have any value because we have missing value. In the second row we have 7. In the third row we have we have 10, and in the fourth row we have 12. So the total is simply 29. We should square all of these value divided by T minus 1 multiplied by T minus 2 all squared. This is the calculated value for the SS for the treatment. This is capital G. This is R1. This is C4. This is T minus 1. And this is T sub K, which is T sub B divided by T minus 1 multiplied by T minus 2 all squared. So if you proceed, the SS for the treatment adjusted This is the initial SS. So we need to modify this SS by reducing it by 1.36. So the SS for the treatment after the adjustment is equal to 69.27. So the value for the SS for the treatment has been reduced. So now we return back. We should adjust for the SS for the treatment. This is the new value for the SS. Notice that the SS for the rows and the columns haven't changed, while for the error it is changed. So because the SS for the total doesn't change, so the SS for the error will increase by the value of the reduction in the SS for the treatment. And another modification or adjustment, we need to subtract 1 from the degree of freedom for the error, which means that we should again subtract 1 from the total, simply because we have a missing value. So now the mean square for the treatment will change, and the mean square for the error also will change. So for the mean square of the treatment, this is the adjusted value for the SS for the treatment, and no change in the degree of freedom. So this is the final value for the mean square of the treatment, and for the error, this is the new value for the SS of the error. And notice that we reduce the value of the degree of freedom by 1. So the new mean square for the error is simply 2.46. Again, the value for the F statistic also will change. So the F for the treatment, we should divide the mean square for the treatment by the mean square of the error. So this is the new value for the mean square of the treatment, and this is the new value for the mean square of the error. So the value for F for the treatments is simply 9.39. The last thing is to determine the value for the F critical. Again, regarding the probability, we have no change. And for the first degree of freedom, also no change. But notice for the second degree of freedom, which is the degree of freedom for the error, it is reduced by 1, so it's 5. So we need to determine a new F critical for the treatment at 0.05 probability, and degree of freedom 3, and degree of freedom for the error equal to 5. So this is the degree of freedom for the treatment, and this is the adjusted degree of freedom for the error, and the intersection is simply 5.41. So the F critical for the treatment is equal to 5.41. So this is the adjusted Latin square table, which is the recommended one Notice that the values that changed has been colored in red. The SS for the treatment, it is reduced. The SS for the error, it's increased by the same amount. The degree of freedom for the error is reduced by 1, and the total is reduced by 1. So this is the recommended and the final results needed for this question. And if we try to make the conclusion, we see that the value for the F statistics is greater than the value for the F critical for the treatment. So for the treatment, we reject the null hypothesis and accept the alternative one. And the alternative hypothesis for the treatment states that the means are not the same, or at least one of the treatment means is not the same as the others. So we have a significance at level 0.05. This is a comparison between the initial Latin square table in the above table and the below one, which is the needed table, which is the adjusted Latin square table. So this is all for the Latin square design, the incomplete design, or the design which includes some missing value. Thank you for your watching, and goodbye.